Hello everyone, and welcome back to the Kohi Game Engine series. Today we're going to expand on what we built last week with our uniforms and take a look at a different sort of type of uniform, if you will. I would like to take a quick second and thank the supporters of the channel, beginning with our partners, Eearslya, Wensheng, Caden, and Patrick. They are the partners of the channel, which is the highest tier of support for the channel, so thank you very much for that. And I would also like to thank all the other supporters listed here on the screen. Your support is very much appreciated, so thank you for that. If you're interested in supporting the channel, you can find links in the description to YouTube memberships, as well as my Patreon page, which is patreon.com/Travis Vroman. So last time we built in the capability to be able to generate a projection matrix and generate a view matrix and move that dynamically over time and have it sort of zoom out and all that stuff. So today we want to expand that a little bit and add in the model matrix that I mentioned. So just as a refresher as to where we left off, this is what the application does now. And so I'm actually going to stop this from moving dynamically, and I'm just going to set this to a value of, say, let's go with -30.0f. Okay? And I'm going to remove this because we don't actually want this to move every frame for this next test. Okay, so let's build that. Let's just verify. And that's pretty good. I think that's far enough away from the square that we can see everything. Okay. And so today we're going to take a look at actually filling out the model matrix. So currently we do not have a way to do this. We only have the update global state, which includes the projection and view and some other stuff, but it does not include a model matrix. So what we're going to do is create an entry point for that to be able to insert that data as well. So the first thing we'll need to do is at the shader level, we'll go to our Vulkan object shader. And I'm going to create a new method, and this is going to be somewhat temporary because we are going to wind up having to move this one later, but that's fine. So I'm going to call this Vulkan object shader object. Okay. And just like the other methods here, we are going to take in the context. And in this case, we are just going to take in a mat for model. And that's all this is going to take for right now, right? This is just going to set the model for right now. We'll expand this as we go on. Okay, so let's go to our object shader, .c, and we'll go ahead and put this at the bottom. And the first thing that we're going to do is we're actually going to go ahead and reuse some of this logic up here. So I'm just going to copy from this global state here and move it down here. We're going to take the image index, and then we're going to take a pointer to the command buffer, right? And we're going to call vk command push constants. And I'll explain what this is and what it does here in a minute. That's going to take the command buffer, and then it'll take the context you know what? I actually need to add one more thing here because I don't want to do it this way. One more thing we need to add here is a pointer to the shader itself that we want to update. So we'll put that in the middle. So we have context, shader, then model, right? So let me go back here and add that here. Okay. So the next thing that this needs is the shader pipeline layout. Okay, and then the shader stage is going to be vk shader stage vertex bit. Okay, the offset is going to be 0. The size is going to be size of mat4, right? Because we're just pushing a single value. And then next it wants a pointer to the values themselves, which are only pushing one value, so we're just going to send the address of model. Okay. All right, so let's back up for a second and have a look at what we're actually doing here. So we're calling this VK command push constant. What is a push constant? A push constant works a little bit like a uniform, except for the fact that it could work without descriptor sets and all the overhead of descriptor sets and all the weight of that. It's typically used for frequently changing data. So it can be basically executed at any point. It does not necessarily have to be in a render pass. And so this is what we're going to use to push the model matrix to the shader, because that's constantly going to be changing, and we don't want to have constantly be writing descriptor sets for that, right? So this is one thing that you'd use a push constant for. One thing I do want to note about push constants is they do have a size limitation. The Vulkan spec only guarantees 128 bytes for the push constant. So every driver that implements this must at least provide 128 bytes, but they don't have to provide any more. So with that in mind, as far as I'm concerned, it has a limitation of 128 bytes. I will never program anything over that, just so that I don't ever have to worry about that, okay? That's guaranteed by the spec. And so what we're doing here is we're just using this as an example of how to use push constants, okay? In order to use push constants, we have to make sure that our pipeline is actually configured to use push constants. So I'm actually going to go to vulkanpipeline.c and look for our pipeline layout, which is here. And right above where we are actually putting in our descriptor set layouts, I'm going to go ahead and add something here for push constants. Okay. So what we need to do is define what we're going to call a push constant range. Okay. And so we're going to call this push constant. The stage flags is going to tell us that we only are ever going to use this in the vertex bit. I don't believe we ever need to use this in the fragment bit, but we can always come back and change this if we need to. The offset I am setting basically to 0. I'm doing the size of mat4 times 0, just in case we ever wind up changing this offset range for some reason. We'll have that alignment there. And then the total size of the push constant that's available is actually the size of 2 of these, which is 128 bytes, okay? And so in order to use this, we'll need to add to our pipeline layout create info a push constant range count, which is just 1. We only have 1 of those. And that is going to be this one, which is push constant. So we just pass the address of that to this array here. And now we can use push constants, okay? All right, so there's not a whole lot that goes into the setup of push constants, actually. That's pretty much it. The only thing that we need to do is wire this up to go further up the chain so that we can use it at the renderer front end level, okay? So what I'm gonna do is I'm gonna take this and add it to our renderer types backend. And I'm actually gonna put this down here. And I'll just rename this to update object for now, right? And the update object at this level is actually just going to take in just the context and the model. And so we'll wire this up to actually call our shader method underneath, okay? And so I'll just convert this to a function pointer, right? And now we have update object available. So I'll take this and I will go to our Vulkan backend, and I will create a new method here, and I will call this Vulkan backend update object, okay? And I'll go ahead and go back to the renderer backend C file and hook this up here. So out renderer backend update object equals Vulkan backend update object. And of course, I'll need to take this and zero it out down here. Okay. And so now that is hooked up. What is this complaining about? Nothing. Okay. One more thing is we will go to our Vulkan backend here, implement this in our C file. So I will go above the private methods here, and I'll put this right there. Okay. And for now, all I'm going to do is say Vulkan object shader update object, and I'll simply pass through the context, and I'll use the context dot object shader. We'll need the address of that, and then the model, which I will pass through a copy of that. And for now, that's all that's going to do. Obviously, we'll have to expand on this later on, but for now, that's basically all it does. So we have that hookup there. That's all wired up. The only other thing that we'll need to do is on the front end, we will need to go ahead and make a call to the back end to update the object. So that is going to entail us going here, and after we update the global states, we will go ahead and call backend update object, and let's see, the context, why is that saying error type? Does that not have, oh, you know what, let me go to this function definition. This actually should not be passing the context here because this doesn't know what the context is. So I'm going to delete that, and actually I'm going to try just using this by itself. So let me go to Vulkan backend, get rid of the context, get rid of the context here. Because we have a statically available context, I'll use that one instead. Okay, and then this is not a pointer. All right, so with that, back to the front end. So this just requires the model now, right? So what we're going to do is we're going to create a mat4, and we'll call this model, and we'll say equals, and we'll use this mat4 translation, except we'll just set it to all zeros for right now. Okay, and then we'll pass the model to update object. All right, and so theoretically what we should get here is absolutely no change whatsoever. So let's go ahead and build this. And it should pretty much present us with the same result on the screen. And it does. So that's what we expect. Great. Okay. Now, there's a couple more things that we need to do on the shader side of things so that this can actually be used. So in the vertex shader, we actually need to add one more thing. So we have here the global uniform object, right, with its layout and all that. However, we need to add something for our push constant. So our push constant has its own declaration, and that push constant looks something a little bit like this. Okay, and here I'm just making a note that it's only guaranteed to be a total of 128 bytes, right? So we're using 64 of those bytes here. So we have layout push constant, and then this is a uniform push constants, right? So again, we're treating this as a struct, right? And we're just calling this push constants, right? And so in order to actually use this, we need to access this model matrix. And then we need to plug that in here. If you recall where I said the model matrix is the last thing to be multiplied in. So we say uPushConstants.model. Okay? And now that will be good to go. So I'll go ahead and run the post build task. And that built successfully. Okay. We've already built our application, so let's go ahead and run one more time. And it looks like we actually have some errors here, but this still seems to actually work properly. So let's have a look at what errors we got. So draw indexed says it uses a push constant statically, but VK command push constants was not called yet for a pipeline layout, blah, blah, blah. So it looks like it might be an order of operations thing again. And actually, I think I know exactly why this is happening. So this is going to be something in our renderer front end. Actually, this is going to be in our back end. So we have in our back end, so let me find it, our call to update global state. And again, our temporary test code is in the wrong place, right? Because we're calling this shader update global states, and then we are, again, drawing our object, right? But we're drawing our object in the update global state, which now makes no sense, right? But we didn't have the function to put this in before. So this is to draw a specific object. So I'm actually going to cut this out of here again. And instead, when we do update object, I'm going to put this in after that. Okay, and that will ensure that this gets called first, and then we go ahead and draw our object, right? And eventually this draw code will not exist here at all. It will exist somewhere else for the specifics of drawing a different object or the different object types. But you know, for now, until we have some of that scaffolding set up, we're gonna have to move this around a little bit. We don't have command buffer and some other things, so let me go and grab that, which is just going to be this right here. So I'll copy pasta that, I'll put that at the top, and now we should be good to go. So let me go ahead and rebuild. Okay, let's go ahead and run, and it looks like something else has failed. So let's scroll down to the bottom here. We don't have any errors per se, so that is actually interesting. Command buffer is empty. Oh, because this is saying that command buffer is null. So why would this be null? So our context, graphics command buffers, so let's go ahead and have a look at the data in there. So I know that there's 3 of those, so we'll go ahead and comma 3 that. All right, so it looks like these all exist from what I can see. They all have handles, okay? So why would this be null? It's taking the address of the first index. You know what? Just to be safe, I'm going to clean and rebuild, because maybe something didn't rebuild properly. Yep, that's what it was. Okay. So we have what we expect here. There was nothing wrong with the code. It just needed to be completely rebuilt for some reason. I'll have to sort out why that is. Anyway, you'll note here that there's no visual change, which is exactly what we are expecting. However, we do know that our push constants are working because we actually got errors when we tried to use them. So we know that's working. So to prove this, I'm going to go back into the front end, and we're going to modify our model a little bit, right? So what we're actually going to do is we have our model here. Okay, and so we're actually going to change up our model matrix a little bit, and we're going to do some rotations. So we're going to take a rotation by saying quat from axis angle, right? And our axis angle we're going to use is forward, right? So we're basically going to rotate this on the axis that's facing into the screen. Okay, and we're going to rotate just a little bit at a time, and we are not going to normalize it, right? And so we're going to take that rotation and call quat to rotation matrix, right? And that's going to take our rotation. And the center is just going to be vec3 0. Okay. And we're going to set that actually to our model instead. So the next thing I'm going to do is similar to what we did with the position up here. I'm going to declare a static f32, and I'll call this angle, right? And I'll say it's equal to 0.01f. And every time this is called, oops, that should be f32, not f42. Every time this is called, we're going to say angle plus equals 0.1f. Okay, and we'll just pass angle here. All right, and so every time this is going to create a new rotation, right, a quaternion rotation, and it's going to create a matrix from that, and it's going to set that as our model matrix. So let's go ahead and build this and run. And we can see that it spins stupidly fast, but it spins, right? So we know that our model matrix is actually working properly. So let's actually go ahead and slow this down, right? We'll slow it down by like a factor of 100 and rebuild real quick, just so we can kind of see it a little bit more clearly as to what's going on. Right, so now we can see quite clearly that our cube is rotating as we expect, right? And so how do we prove then that that is not just the view matrix like rotating or something, right? How do we prove that our combination of these things is working properly? Well, we can put back our handy dandy little method here. So we can put back static, and then we could say f32, we'll call it z again, right, equals 0.0f, and then we'll say z minus equals 0.01f, and plug z back in here, right? And I'll just leave that 30 in a comment so we can put that back. Build and run, and now we see that it rotates and our camera is moving away. Now obviously this is just a contrived example. This isn't doing anything overly complex, right? But what it is doing is it's showing that our system is working, right? And so eventually we'll actually be setting this up with a proper camera to feed in these projection and views so that we can move around with the keyboard and mouse and so forth. And we'll actually wind up probably doing that very soon. So let me stop for a second and kind of explain a little bit what is going on with all these matrices, okay? So the best way to do this is probably to start in our actual shader, right? So I'll pull up the shader, and we'll see here that we have these three matrices being multiplied by the position, okay? And so the way that this works is the projection matrix takes the three-dimensional positions of everything and flattens it to our two-dimensional surface, right? And it does that in such a way where it makes objects in the distance appear smaller, right? And that's what that W component does in that projection matrix. If you were using an orthographic matrix, it would appear completely parallel and objects would not scale down and get smaller as they go away from the camera in space. But in our case, we're actually just using a perspective matrix, and that's where we get that, right? So our projection matrix takes that three-dimensional world and flattens it to 2D to something called normalized device coordinates, which is a range from -1 to 1, both on the X and Y axis, right? So you can think of it as your flat screen here, right? So -1 is here, and +1 is here and here, right? And so the projection matrix is what's responsible for that. And those normalized device coordinates, incidentally, are what we were originally rendering in. So if we go back to our Vulkan backend and we go up to where we were uploading our geometry, right? Our original value here was 0.5, right? And the reason for that was because without the projection matrix, we were just using normalized device coordinates, which is why a 0.5 to 5 triangle showed up so large on the screen, okay? And so by switching it, we switched away from that -1 to 1 range to a range that is more appropriate for the resolution and aspect ratio of the screen. And so we had to multiply this by a factor of 10 to get the thing to actually show up properly on the screen so that we could actually see it, because once you apply that projection matrix, something 0.5 is a little bit harder to see. We still would have been able to see it, but it would have been pretty tiny on the screen, okay? And so that is basically what the projection matrix is doing for us. The view matrix we're actually not technically doing correctly yet. The view matrix is a representation of the camera, and ordinarily it's the inverse matrix of your position or your camera's orientation. And so right now we've sort of got that hard-coded. And so if we actually look at the Vulkan backend and we browse to the relevant code, I'm sorry, it's not the backend, it's the front end. Right here, we are just basically taking a translation. And if you recall, I started this off with a negative value, right? However, in our case, negative is actually into the screen, but you'll notice the further that we actually move in the negative direction, we're moving backwards out of the screen, if you can think of it that way. So we're actually moving away from that quad, right? And the reason for that is because we should be using the inverse matrix of this, right? So if we were to take this, right, and we were to just plus it instead, right, and then take the view and say view equals mat for inverse, and that's going to be of the view, okay? And we were to actually build this out now where it's actually going a positive direction, we'll see the same thing. Right, same result. So, you know, technically we weren't doing that correctly. Now we actually kind of are doing that correctly because we're properly taking the inverse of the matrix. And so that's a proper view matrix, okay? So you can't ever just take the camera's orientation and use that as your view matrix. You're supposed to take the inverse of the camera and use that instead, okay? Great. So now that we have that, finally we have, if we go back to our shader here, finally we have the model matrix, and this is the object's orientation, right? So this is what we're rotating to make that quad sort of rotate in space. We're rotating the model matrix, okay? And so your matrices are all multiplied against one another, and then this vector 4, which remember a vector is also a matrix, it's basically just a 1x4 matrix, is our position here, and we're taking that and multiplying it this way, right? And so the order of this matters because that transformation matters, and this GL position is ultimately what gets output to the fragment shader, which becomes written to the screen or texture, okay? And so you can think of it as being processed from right to left, right? Great. So I hope that makes sense. I hope the at least high-level explanation there of what these different matrices do and why they exist the way that they do helps you understand a little bit more of the way that the objects are actually transformed to go from the 3D environment to the 2D environment. And so I think this is probably where I'm going to end this video for right now. Before we actually add things like textures to our scene and lighting and things like that, I think it's actually fairly important to be able to navigate the scene from early on. So in the next video, we are going to go ahead and proceed with that, and we are going to go ahead and make it so that we can hook up some keyboard controls to be able to look around our scene a little bit and not just be sort of locked in one place, okay? So with all that said, thank you guys very much for watching. I hope you enjoy this series. I hope you learn. If you have any questions or comments, feel free to leave it in the comment below. Also, don't forget, I do have a Discord server. There's a link to that in the description below. And if you liked the video, please hit like, give it a thumbs up. If you haven't already, consider subscribing. Click the little notification bell there to get updates as to when the next video in this or other series drops. And I will see you guys next time.